Hey guys, welcome back. In this video, we'll talk about hydrolysis. And the question is, what happens when a salt dissolves in water? And a salt, of course, is any ionic compound. All right. And so for our example, will be sodium fluoride. All right. Well, the first thing that happens would be the salt has to dissociate. All right. That means K. So if I come down here and we have K and F, and it's a solid, right? The first thing it has to do is go to K plus and F minus. Right? So we have the two ions. It has to break up. The second thing that would happen, it has to be solvated. All right? Okay. What does that mean? That means we get the AQ here. All right. So what does that mean? All right. And so if I have a potassium ion and a fluoride ion, all right, to be solvated, they're going to have water around them. Now, a lot of times these small ions have 6 or so waters around them. All right? And so since potassium is the positive side, you'd have O going towards. A lot of times they write it H2O like this way, or OH2. All right? And so you can put the lone pairs on there if you want. All right? And then fluoride, of course, even though it's bigger, it still only has 6, but it's the H's are around fluorine. Kind of if that makes sense to you guys. All right? So that's a solvated ion. And number 3, the third thing that could happen would be hydrolysis. And that's maybe. Maybe hydrolysis. All right? So you guys know salts dissolve, right, with almost complete dissociation. Provided the solution is dilute and the salt is soluble, right? Right, so what does that mean by that? If you guys ever gargled salt water, right? So you had sodium chloride from the, whatever salt you had in the cupboard or the shaker or whatever, and you put it into water. You can put more salt into the water than dissolves, right? At 25 degrees Celsius, it's like 35-ish or 38-ish. I forget the exact number. I have it somewhere, but I don't know exactly where. Coming up in a few, right? So I think, I don't know exactly what it is. It's around 35 grams per 100 grams of water. At 25 degrees Celsius, I believe. And so we can put more in there, right? So as long as you're below the solubility threshold for sodium chloride and, right, the salt's soluble, right? So if you put calcium carbonate, right, like your sidewalk chalk, if you put that in water, it's not going to dissolve, all right? Okay, now, assuming that we have a soluble salt like sodium fluoride or sodium chloride, but our sodium fluoride is our example. Although I put down potassium, so we'll change that to potassium. All right. Okay, so now, when we talk about the salt dissolving, the solution's dilute, salt soluble, the ions produced are either solvated or we can call hydrated by the water molecules. And this makes sense, doesn't it? Right? Because you're going to get into water, you're going to get wet. Right? We're just looking at the particle level now. Right? Because if you looked at, you throw anything into water, it's wet. Right? You're surrounded by water. That makes sense. But on the molecular level, right, in the atom or ion level, we're looking at how water and the ions are actually interacting. So we're looking at a very, very micro scale. Now, in some cases, right, the solvated ion right, may react with the water in a process called hydrolysis. Right? This happens when the salt is a salt of a weak acid or a weak base. All right, so we have our potassium fluoride here, which is fine. It's a good example. One of these probably will undergo hydrolysis. Otherwise, we'd have a very bad example on the screen here, on the paper. And so now, which one undergoes hydrolysis? So if you look at these two, K and F, K comes from KOH, right? That would be the base, potassium hydroxide, right? And this is a strong electrolyte. Right? Because it's a strong base. What we have here, fluorine, right? HF. And that is a weak acid. All right? That's a weak acid. And so what we have going on here, we have, this is Bronsted-Lowry. That's the definition we're going to be talking about, right? Right? It's a competition for the proton, or the H+. Right? And sometimes the fluoride gets the proton. All right? That makes sense. All right. Hopefully that does make sense. Okay? And now, when we look at this, F minus plus our water, our reaction with water, H2O. You get HF plus OH minus. All right. So that means, and we already know this, fluorine, or fluoride, excuse me, is a base. Right? This is a KB. concentration of hydrofluoric acid, concentration of hydroxide, all over the concentration of fluoride. All right? And so we now know that potassium fluoride, the potassium is a neutral salt. We call this neutral because it's from a strong electrolyte. But the fluoride is not neutral, right? It's a base, okay? So now, how do we know which one of these ions undergoes hydrolysis? That's a great question, isn't it? All right. And so the question would be, all right, how do we identify these things? How did I know? Well, think of it if you have a no hydrolysis team. Who's on the no hydrolysis team? Well, the cation, well, let's do the anions first. You got chloride, bromide, iodide, right? Because you got hydrochloric acid, hydrobromic acid, hydroiodic acid. Those are strong acids. You got nitric acid. You got perchloric acid and chloric acid in this class. Now, note HSO4, hydrogen sulfate, is a weak acid. So even though sulfuric acid is one of your strong acids, HSO4 is a weak acid. Now it's actually got a pretty large Ka for a weak acid. Now, cations. You got lithium, sodium, potassium, rubidium, cesium. Beryllium is not going to be on that list, but you're going to have magnesium, calcium, strontium, and barium. All right. All other cations are Lewis acids, right? And they will be acidic. What do I mean? Well, we got like aluminum, AlH2O6. This has a Ka of 1.3 times 10 to the minus 6. So what goes on the other side? It's a great question. All right? So if you have your aluminum ion, right, you'd have your waters right around here. So I got OH2, OH, H2O, 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 H2, right? Okay. Now it's symmetrical, right? But what's going to happen is that one of these, now it could be any H, right? Okay, there's 12 hydrogens. Any one of them can go off. They're all symmetrical. And one of these hydrogens is going to come off and go to water. And so on the other side, you're still going to have H3O plus. And you have your Al. Then you'll have your hydroxide in there, OH. Then you'll have your H, well, depends on how you write it, H2O 5, 2 plus. Sometimes you might write it Al, H2O 5, OH 2 plus. There it is. Either way you want to write it. I'm not going to pick you on that. And so what happens on the other side here, you have your aluminum. That's the square. Okay, perfect. We'd have our, let's say OH there. Where's And then we have our waters around the rest. Oh, wow. Let's go with H. No, OH2 is right. All right, perfect. So that's what we have. So now, some questions, some examples. 1, what is the pH of a 0.10 molar solution of potassium fluoride? Now, I'm going to give you hydrofluoric acid's Ka is 6.8 times 10 to the minus 4. So what do? Well, we recognize, first of all, that K is neutral, and fluoride is a base. So we would have F minus plus water going to HF, hydrofluoric acid, and hydroxide. And I'm going to do it this way. All right, so ice table. Start off with 0.1 molar fluoride. Don't care about water. None. And we're going to start with none. Even though technically you have 1 times 10 to the negative 7th, we're going to start with none. Sum is going to change. Minus x plus x plus x. So we have x, x, and we have 0.1 minus x. Your KB expression, HF, hydroxide, all over fluoride. So KB, remember Ka times KB is KW, right? So that means KB is KW over Ka. Well, KW is 1.0 times 10 to the negative 14th. Ka is 6.8 times 10 to the negative 4th. So that means KB, get our trusty calculator here. 1 times 10 to the negative 14th divided by 6.8 times 10 to the negative 4 is 1.5 times 10 to the negative 11th. All right, let's plug it in. 1.5 times 10 to the minus 11 equals, I'd have x squared, hopefully you guys are getting good at these, all over 0.10 minus an x. Well, you can approximate here. What are we approximating? We're approximating this change is negligible, all right? Because the initial concentrations 10 to the negative 1, and the K value, 10 to the negative 11, were 10 billion times bigger, all right? That's a big difference. So we're going to approximate this. 1.5 times 10 to the negative 11 is approximately equal to x squared over 0.1. Well, if we multiply by 0.1, we get 1. Well, that's not going to do blue. 1.5 times 10 to the negative 12 equals x squared. So the square root of 1.5 times 10 to the negative 12. I get 1.2 times 10 to the negative 6. And that's what we want, that x right there. All right, how do we calculate the pH now? Again, there's 2 ways. Most students like to do pH plus pOH equals 14. So that means the pH equals 14 minus the pOH. So pH would equal 14 minus the negative log of 1.2 times 10 to the minus 6. So the pH would be 8.1. And that's what I get for that. That's not bad, huh? It's not a lot, but it's an order of magnitude more hydroxide than it would be if it's neutral water. So it's measurable, very measurable. All right, so the pH is affected by sometimes salts. All right, number 2. Which of the following solutions are basic? Great question. All right, so we're going to have 0.5 molar sodium chloride, 0.5 molar ammonia, 0.5 molar potassium cyanide, 0.5 molar ammonium chloride, 0.5 molar sodium acetate. All right. So what do we have here? Let's look at the first one, sodium chloride. This is strong, and this is also strong, right? NaOH, HCl. So this is neutral. This one would be neutral. Ammonia, that's your weak base. So this is basic. That's your weak. That's a weak base. KCN, strong. KOH, CN, HCN, weak. So CN minus, is that a proton donor or a proton acceptor? Well, that's a proton acceptor, isn't it? That means this is basic. Ammonium chloride. That one's strong. Chloride strong. But ammonium, NaH4 plus, that's a proton donor. It means it's acidic. So that one's not basic, it's actually acidic. Sodium acetate. Sodium, that's NaOH, it's strong. Acetate is a proton acceptor, right? Because you can make HC2H3O2. It's a weak acid. So this one also would be basic because acetate can accept a proton. All right, so that's that. One more example is sodium hydrogen sulfite, an acidic or basic? It's a great question. All right. So for H2SO3, Ka1 is 1.3 times 10 to the negative 2. And Ka2 is 6.3 times 10 to the minus 8. All right. So this one is a little bit more involved. What do you mean? Well, sodium, right? We break up right here, right? And Na plus is neutral. So we have HSO3 minus in solution. Well, we can add this with water. And what happens? It can be a proton donor. Get H3O plus and SO3 2 minus. And that has Ka1 involved. No, Ka2, excuse me. Ka2. That's the second proton. 6.3 times 10 minus 8. So we know how far that reaction goes. So this would be acidic if this is the case. However, basic can also happen. What do you mean? Well, HSO3 minus, hydrogen sulfite with water. Could it not go back to H2SO3 and hydroxide? I believe it can do that, don't you? So if it can do that, what's the value? Because we need to compare the value now for that. Well, my recommendation at this point is to write the Kb expression, because which one of these two K values would we use to calculate this K, right? Because this Kb is going to be equal to Kw over one of the Kas. Which one? Is it Ka2 or Ka1? That makes a big difference. So Kb here would be equal to H2SO3 hydroxide all over HSO3 minus. Well, I need the Ka, right, that would multiply by this Kb to cancel out. I need to cancel out, right, sulfuric acid and hydrogen sulfite. Well, if I use Ka2 here, which this is Ka2, right, I would have sulfite in Ka2, and Ka2 would not cancel out this Kb. I'm going to have to use Ka1. So let's just write Ka1 down, right? Ka1 would be H2SO3 plus water going to H3O plus HSO3 minus, right? And so Ka1, concentration of hydronium, HSO3 minus, and H2SO3. And so if I look at Ka1 here, I need Ka1 to make this work. Right, so if I use Ka1, cancels and cancels, cancels and cancels. And I'm left with those two, which is what we want. All right, so Ka1's value was 1.3 times 10 to the minus 2. So that means this Kb would be 1 times 10 negative 14 divided by 1.3 times 10 to negative 2. I got 7.7 times 10 to negative 13. All right, so now for the acidic reaction, Ka2 is the equilibrium constant 6.3 times 10 to the negative 8. For the basic reaction, K is 7.7 times 10 to the negative 13. So Ka2 is bigger than Kb, right? So if you look here, Ka2 is greater than this Kb we just did. So that means Ka2, the reaction goes further. So that means this reaction, this is going to be acidic because Ka2 is bigger than Ka1 or Kb1. All right? Because Ka2 is bigger than the Kb. All right? Hopefully that makes sense. All right? So we look for whatever, right? The bigger K means the reaction goes further to completion. So since Kb is significantly smaller, right? It's negative 13 and negative 8. Right? So if you think about that, it's 5 orders of magnitude larger. Ka2 is 5 orders of magnitude larger. Right? So just that's a huge number difference. So hopefully that works. If you have any questions, feel free to reach out. Otherwise, we'll see you in the next one. Take care.